Welcome to the last plenary talk of the conference, and it's much appreciated that you are all here this early in the morning, considering the late time it was yesterday after the dinner. So that really shows you are interested in the topic. So today's speaker is definitely worthwhile to attend a plenary session early enough in the morning. It's Professor Giuseppe Notarstefano from the Department of Electrical, Electronic and Information Engineering at the Università di Bologna in Italy. Let me briefly introduce his background. So he is Italian, which is kind of obvious from the name. So he got his laureate degree in Pisa, then moved to Padua, where he got his PhD degree with Ruggero Frezza. And during his PhD, he already had a stay abroad, or several stays abroad, and that he continued also after his PhD. So he spent quite some time in Santa Barbara at University of Colorado in Boulder, and he also spent a couple of visits actually to Stuttgart University that we very much enjoyed. After that, he was immediately hired as an assistant professor at the University of Salento in the south of Italy, in Lecce, where he was first assistant professor, then became associate professor, and last year in July he switched to Bologna. They decided that in the south of Italy it's too hot, probably. I can second that. His expertise is optimization, distributed optimization, optimization over networks, optimal control. He has also very interesting application interests, but I'm sure he will show us much more about that. He received quite a number of awards already. Let me also only mention one thing. He has an ERC starting grant that he is working on, and he will talk today about optimization in networkland. And without further ado, Giuseppe, we are very much looking forward to your presentation.
Okay, so thank you, Frank, for the very nice introduction. Actually, it's really an honor for me to be introduced by you for this plenary. So thank you for coming, to be so brave after yesterday. And seriously, let me thank the organizers, because it's really an honor for me to be a plenary speaker for such an important conference and such a successful conference. Since now I'm at the last day, I can say it was really successful to me, at least. Okay, so let me start. Let me get started. So let me start from the title. So this, let's say, fancy title. So when Mario and Kalle asked me to give a title, I decided to use this optimization in networkland because it's really what I had in mind when I started to run this project on distributed optimization. And the reason is that I really like to think of distributed optimization as we have this very strong discipline, which is optimization, which traces back really in the history, and that plays a really key role, important role in several fields, not only engineering. There are a lot of methods that nowadays are standards in optimization, but still it's an active area. But then our community started in early 2000. It was 2003, 2004. I remember it very well because I was starting my PhD. It started to get involved in this network world. So a world in which you have several devices that can compute locally and communicate. So now for us, this is a well-established word, but what was the motivation for starting in this world, not only our community, but also other communities, was that really there is this massive and spread computation capability technology nowadays, in which there are a lot of data that often want to be private. And the idea is, okay, so we want to do some control processing computation or optimization, but we want to do it without disclosing data. We want to share the computation rather than the data. And so distributed optimization really comes nicely by putting together optimization with this network world. And therefore, when we started to work in this area, to think of what are the challenges in this area, it was simply a point of taking all the challenges from the distributed computation world and look at what are the challenges in optimization. So this is what I will briefly describe in the next slides. So let me start from, let's say, the challenges in distributed computation. So we all know now, after 15 years, that for us a distributed algorithm is an algorithm in which we have agents. Each one does some local computation and communicates with neighbor. Computes locally, communicates with neighbors. And so we started, for example, with very simple problems. So the key challenge of distributed computation is that even very easy problems, like computing an average, you sum n numbers and you divide by n, becomes a challenging task in a distributed context. And so you can start with a communication graph that is fixed and undirected, and you start to work out solution. Then you go maybe to directed graphs. Then you want to move from fixed graph to time varying graph, in which maybe still all processors are synchronized, a synchronous clock, but then you start saying, okay, if I want to go to real applications, then I should start considering asynchronicity because maybe processors are asynchronous, and this is not even enough because in the concept that we have in mind, you want to consider networks in which maybe you can drop loose packets or edges can be dropped. So the key point I like to stress when I give talks on distributed, let's say, computation, or in this case, optimization, is that differently from what people consider the distributed protocol in the past, for us, the topology, the communication is not a design parameter. So when we design algorithms, we do not want to design the network protocol. So the network is something that comes from the environment, and we want to design algorithms that work despite or for any possibility of the network, because this is really the unstructured world that we want. Okay, so this is clear for us as a community, but then let's go to the optimization challenges. So you want to solve an optimization problem over a network, then you start think of what people have addressed in the past for an optimization problem. So you have to minimize a cost function subject to constraints, and then you start saying, okay, let's maybe start from a convex problem, which are, quote, easy problems to solve maybe. But then you start saying, okay, maybe I don't want this convex problem to be smooth. Maybe I start adding no smoothness. Or then I start to move to non-convex problems. And if I want to go farther, I can say, okay, maybe there are even more challenging problems in other areas, as, for example, combinatorial problems in which the decision variable is discrete, or maybe even more mixed integer problems in which you have both discrete decision variables and continuous decision variable. So classical challenges in optimization, and then you have to think of them in networks. Then for optimization problems that arise nowadays in these network systems, there is another very interesting challenge that is the size of the decision variable. So I will show you that there are interesting problems that for which the dimension of the decision variable is very high, and people like to call these problems big data, if you want to use, let's say, a very timely wording, or sometimes also huge scale optimization problems. And I will show you that in some cases, this dimension is related to the number of agents. In other cases, you may have a high number of agents, but also a decision variable that is very high dimensional. And then other challenges that I think are really something that we need to address, that are very important challenges, especially for us in the control community, which is the fact of solving problems optimization problems that are somehow dynamic, like, for example, optimal control, so problems in which you have somehow a time horizon, and maybe you want to solve them iteratively. Think of, for example, MPC schemes. So you have to think of solution, keeping in mind that you want to solve many of these problems. And something that, as we saw in the other plenaries and as we saw in many of the sessions, is becoming really very, very important due to this data-driven idea coming from machine learning, is the idea of addressing problems that are stochastic or in general uncertain, so in which you have uncertainty in the problem. This is, I think, a key challenge that still needs a lot of work. So you combine these challenges from the network and from the optimization, and then you really have an amazing research area in which you can really enjoy doing a lot of things. So let me get into more technical details. So let me start formalizing what we mean by a distributed optimization problem, or solving an optimization problem in a distributed way. So the idea is the following. You have these two ingredients, the optimization problem and the network. But the idea is that you cannot think of a very general optimization problem with that form. So you have structured optimization problem. And the idea is that in these structured optimization problems, each node only knows a piece of the optimization problem, a portion of the optimization problem. And I will clarify what I mean in the next slides. So let's say two ingredients, a structured optimization problem in which each node knows only one piece of the problem, and the concept of solving such an optimization problem. So what do we mean by agents solving cooperatively an optimization problem? I will clarify this as well in the next slides. So let me just say that in distributed optimization, we somehow make standing assumptions that agents are cooperative. So we don't deal with game theory. That's another very challenging and interesting research line that people are pursuing now. Okay, so I said, let's see, we have structured optimization problem that somehow are mapped into the network. So let me start with a first class of problems. I like to call them cost-coupled problems. Sometimes in the community they are called consensus optimization problems. It will be clear in a second. So in these problems, you have to minimize the sum of n functions, where n is the number of agents. But let me stress that each function is a function of the same decision variable. So for example, in this picture, think of these level curves as the level curves of the entire sum of functions. X is a two-dimensional variable. So in this case, X does not have anything to do, the dimension of X is not related to the number of agents. For example, in this case, it's two-dimensional. And so the agents want to minimize, so find an optimal X star. But how? So the idea is that each agent only knows its own Fi, and agent J knows its own Fj, okay? But all of them, they want to keep a solution estimate of the X star that they want to find. So agent I has some Xi of t, which is the estimate of an optimal solution at iteration t. So I will use t as iteration counter for the algorithm. Okay, so now what does it mean that they want to solve this optimization problem in a distributed way? Then it comes naturally to say that all these estimates need to agree asymptotically as t goes to infinity to some X star. So this is the idea. So in this problem setup, solving the problem means reaching consensus asymptotically to an optimal solution for all these solution estimates. So did we just invent this setup because it was easy to start finding results in a distributed setup? Did people do that? No, that's not the case. So these problem structures were out there much before distributed computation came out. So for example, let me give you an example. So this class of problems is really very common in signal processing, machine learning, estimation in general. So think of a very simple data regression problem. So you have some data, some points, and you want to find somehow the best fitting using some quadratic distance. So now think of a network context in which you have many devices. Each device only knows some of this data, okay? So what could an agent do? It could just do the fitting of these few data, but as you can imagine, that would be not very efficient. So what is desirable is to do the fitting over all the data, but as I said, you don't want to disclose your own data. So you would like to compute the same X star, but keeping this data private. And so how can you do that? You can do that by solving this optimization problem in a distributed way, in which you assume that node I only knows its data, and therefore knowing its data means knowing only its own function fi. Okay? But again, in this case, they all want to compute the same X star, reach consensus. Okay, another setup that I like to identify, again, because it has some applications, but also because we could come up with a very interesting algorithm that work in very general network settings, is this setup that I like to call common cost setup. So what is the difference with the previous one? The difference is that now there is a common cost function, f of x. Again, x is a common decision variable as before. But now x must live in the intersection of n sets, and each agent only knows one of these sets. So an example, so think of a support vector machine problem. This is a very common problem in machine learning. So from a mathematical point of view, it's very easy to explain. You have two classes of label points, circles and triangles. They are somehow separated, but you want to find a maximum margin separator, because then when you get new samples, you can classify in a more robust way, okay? So as you can see, this is one of the ways you can write it. So this cost function somehow can be known by all the agents. So there is no private data in the cost function, whereas there are private data in the constraints, and therefore it's interesting to assume that each node only knows one constraint. Okay, the third class of problems, so I will give you three classes of problems that arise in networks. So this is the third one. So let me start with an example to understand clearly what is the difference with the previous setups. So say that you want to minimize the sum of two functions, c1 of x1 plus c2 of x2. But now the decision variable x1 must belong to the set x1 and x2 to the set x2. So two different variables. So if I had only this problem, then I could find a solution without solving the entire problem, but just minimizing with respect to x1 and with respect to x2, and I would get the same point. Now, the problem becomes challenging when you start adding a coupling constraint. So in this case, agents cannot compute the solution independently. You need some cooperation, because you need to satisfy the coupling. So if we then go to a general version of this problem, the problem setup is the following. So you sum n functions, sum of fi, but now each fi depends on its local decision variable xi. So each xi has to satisfy some local constraints, but then all these decision variables are coupled by this constraint. So this is why I like to call it constraint-coupled setup. So let me point out that in this case, the dimension of the decision variable is related to n. So the decision variable is x1, xn, so it scales with n, okay? So, what about what agents know? So each agent knows a piece of the cost function fi, its local constraint xi, and a piece of the coupling constraint. So you cannot think of applying methods for the cost-coupled setup, because you should assume then that all the agents know the coupling constraint, whereas we don't want to assume that in applications. So this setup for our community is very, very interesting, because it arises in many applications. So before going to the applications, let me show you what we mean by solving now this problem in a distributed way. So in this case, there is no consensus, because in this case, it makes sense to say that each agent has only an estimate of its own local decision variable, and wants to converge to that piece of the solution. So agent 1 has x1 of t that converges to x1 star. So the solution is x1 star, xn star. So no consensus here. So a different concept of solving the problem. As I said, it's a problem setup that arises in many interesting control applications. For example, consider an optimal control problem in which you have n independent systems. So the dynamics are all decoupled. Each agent wants to minimize a local cost function. Then you can think of minimizing the sum of the local cost functions. But then you have maybe a coupling due to, for example, some limited resource. So resources are limited, so agents cannot do what they want. So they have to satisfy this coupling constraint. And if you just look at the three ingredients, it's just a setup that I described, where the local decision variable xi is basically the state and the input of agent I over the horizon t. Okay, so as I said, this problem setup arises in many applications in, for example, smart power networks, but also cooperative robotics, and also, for example, the, task allocation problems, and so on and so forth. Now, think of these three setups that I just described. Think of those challenges that I mentioned, and then you can really play with these setups with all those challenges. For example, in this optimal control problem, if you start to have nonlinear dynamics instead of the linear ones that I showed, then the problem starts to become non-convex. If you allow, for example, switching or hybrid dynamics, or if you approximate the nonlinear dynamics with piecewise linear dynamics, then the problem starts to become mixed integer. So again, all those challenges, so think of them in the optimization setup or in the network context, and there is really a large amount of problems that you need to solve. And that's why, for example, in the last conferences, even this one, we now start seeing really a lot of works in this area. So in the next part of the talk, I will try to show you some of the results that we achieved in the last 3 or 4 years. I will show some example in each one of these three setups. I will start with the cost-coupled one, which is the one that historically was born before, and I will show you some of the first algorithms in this setup. By the way, if you got a slip in one of these pieces, you can get back to the other one. So, okay, so let me start with the first one. Again, cost-coupled setup, sum of functions, a common decision variable. Say that we want to solve this problem in a centralized way. So the usual way you play in general in distributed control computation, but especially in distributed optimization, is the following. So let me see what people have done in a centralized setup, and then let me try to emulate that in a distributed context. Okay? So one of the most known algorithms in a centralized setup is gradient method. So here, in the next of the talk, I will assume the most simple setup. Here, functions are smooth. Otherwise, if they are convex and not smooth, you can think of subgradients, but let's forget it, okay? So gradient method, so you update x of t as xt plus 1 equal to xt minus some step size that you can call alpha t, which can change, and sometimes it's needed to change during iterations. And then a direction that for the gradient method is typically a descent direction. So you compute xt plus 1 as xt plus this scaled direction. And for gradient method, in this case, for this function, what is the gradient of this function is the sum of the gradients of the local functions. Okay? So this is what you would do in a centralized setup. Now, can we try to map this one in a distributed context? So first of all, we don't have an xt, but we have n xi of t. And since we want them to agree to reach consensus, then it makes sense so xit or j as xjt. So since we want them to agree on an optimal solution, then it makes sense to say, okay, let's try to implement an averaging consensus protocol. In our community, we have played a lot with this protocol, so we know how to somehow reach consensus. For example, the easiest assumption that you can make is that the weights are doubly stochastic, and people that have worked here know perfectly what it is. If you go to directed network, for those of you that are more familiar, you can go to more involved protocols like push-sum, but the idea is I want to average all the estimates. But then I need to find a scaled direction. But now this is a global quantity, so I cannot use as an agent I that global quantity. I need to use something that is local, some DI, some direction DI. So people have started to think of it, and the first contributions were due by Nedic, Ozaglar, and actually also other people, I think also Cal had something simultaneously at that time. So the idea is the following. What the intuition would say, if I know only Fi, let's use gradient of Fi. The problem is that if I use gradient of Fi, then I'm choosing a wrong direction, because that's not the gradient of the whole function. The gradient of the whole function is the sum. And in fact, you can prove convergence, but this diminishing step size is crucial, because in some sense, the averaging allows you to average the direction, but then at some point asymptotically, you want to turn off this direction because it's wrong. Okay, so that's kind of the intuition. And the nice thing is that in the analysis, you basically prove first consensus to the time-varying average of the estimates, and you can decouple this part due to the diminishing step size. You prove it basically showing that a linear, time-invariant, or time-varying system has some convergence properties. And then, somehow in a decoupled way, you prove that this time-varying average converges to X star, okay? There is really a lot of work in this setup, and there has been a lot of work with this protocol trying to address all those network challenges that I was mentioning. But then people started to say, okay, can we try to do something more sophisticated? So this DI, this direction DI-T, should I really choose it in the wrong way every time, every iteration? Can I try to do something better? Can I try to basically try to track the true gradient of the function? So if we look at the true gradient of the function is the sum of n terms, but then the sum of n terms means that if we divide it by n, that becomes an average. And again, we know how to play with averages with consensus protocols. So what people started to say, okay, let's try to implement what is called a dynamic consensus protocol. So here there is a consensus part, and then you try to track the average of all these gradients. And they came up with this idea of the algorithm. Again, you can put here the same weights and assume that they are doubly stochastic, but then if it's directed, you can use this push sum idea, but then people start to figure out that in fact that's not needed, but this is why I put a tilde here. What you need is this part to be row stochastic and this column stochastic, but these are more technical details. So the idea is the high level idea is what I just explained. And in this case, the nice thing is that since you are not choosing anymore a wrong direction, even asymptotically, so asymptotically you are choosing a good direction, the true direction, then you can use a constant step size and you gain a linear rate. What you pay is that now you need to prove both of them simultaneously, and there are nice proofs, some based on, for example, small gain, some of them based on finding an appropriate Lyapunov function, or let's say Lyapunov-like function, and so on and so forth. So the nice thing was that there are really many groups that started to work with this protocol, but then everyone wanted to have his own name for the algorithm. So if you look around, you will find very fancy names for this protocol, but it's this in different sites. So these methods that I mentioned are based on consensus and are somehow primal methods, but there is a very nice class of other methods based on the idea of duality, decomposition, and so on and so forth. So I will not mention them in this talk, but there is really there are really a lot of papers on that. So let me now show you something addressing one of those challenges that I mentioned. So in the protocol that I showed you before, you typically assume that the decision variable x is not so high, so it can be scalar or it can have some dimension. But what about now if the x has a dimension b, which is very, very high? And here b, in some sense, is unrelated from n. So you can have really many agents, but at the same time, each agent has to handle a very high dimensional decision vector. So we started some work with my postdoc, Ivano Notarnicola, and with a collaboration with Gesualdo Scutari and his postdoc at Purdue University. And the idea was, since Aldo was an expert in this gradient tracking idea, so let's try to implement a blockwise version of that protocol gradient tracking that I just showed. Why blockwise? Because the idea is if the dimension of the decision variable is so high, then you don't want to optimize over all the entire X, you want to optimize over a piece. By the way, some groups call this mini batches. And then even more, you want to communicate only one of these blocks, because otherwise it would be impossible in terms of bandwidth. And so the rough idea was to implement this blockwise version. One of the main challenges that we had to address is that if you now look, so basically what an agent does is picks a block, okay? But if each agent picks a different block at different t, then if you focus on the block, you start having a graph that is directed and time varying, even if you start with a time invariant graph. So you can look at it and it arises naturally. So this provides challenges. For example, we had to use this push sum protocol instead of the standard one, but somehow, I don't want to comment this equation, they are somehow the blockwise version of those ones. So you just optimize over one block and communicate one block. And we proved some result that was somehow the counterpart of the one block case, of course, with many challenges due to the inexact optimization and to this time varying network. Then recently, I started with another postdoc, Francesco Farina, in my group, to address the same class of big data problems, but now we added stochasticity to the cost function. So now the functions are, so we want to minimize some average of some functions. So here we consider the convex case but non-smooth, and we somehow try to emulate the first protocol that I showed you, the distributed subgradient. We did that, again, I don't want to give too many details, but basically you average, just getting one block, and then you do this step, which is the one that I showed, the distributed subgradient, only on one block, and then you communicate again only one block. And again, also in this case, with several more challenges, we were able to find similar result to one block case. Actually, recently, Francesco found also some nice convergence rate that depends, of course, on the block, and then when you get to one block, somehow gets back to the one block case. So I wanted to show also this work, because then we found a very nice application for this. So if you consider an image segmentation problem, so you can write it as a combinatorial problem. So now the decision is discrete. So think of this setup. You have an image and you have n agents. Each one only sees one piece of the image, but then all of them, they want to reconstruct the entire image. So what you can do is to do something that is called a Lovash extension of this combinatorial problem, and you get to a continuous problem, which has exactly the same structure as before. Now this x, the dimension of x depends on the number of pixels of the image, and therefore it can become very, very high dimensional. So it makes sense to apply this protocol, and we were kind of happy to see that it was working quite nicely. Okay, so woke up now. Let me go to the second part. So common cost. So why this common cost setup? Because as I said, it has interesting applications, but also we were able to find interesting algorithms. Again, in this case, common cost function, I'm assuming to be linear, and then an intersection of n constraint. Each agent knows one constraint. So here this is a work that I started during my PhD, so some of you have probably already seen this part several times. So just to give some intuition, say that you have a problem with this structure, a linear program with many, many constraints. So what you can show is that if you are, for example, in 2 dimensions as here, the solution, even if you have like billions of constraints, depends only on few constraints. In this case, 2 constraints. So the idea that we had was, okay, so let's try to exchange among neighbors not an estimate of x star, but an estimate of some optimal basis. So somehow let's exchange active constraints. Let's see what happens. And in fact, you can come up with this algorithmic idea in which you keep a basis, which is an estimate of the optimal one. The other agents do the same. Then you exchange this basis, you collect them. You need to put inside also the initial constraint, and you solve a smaller version of the original problem. You do it, and you compute a new basis, and then you send the basis again, and so on and so forth. And then what we were able to show is that you have, for this algorithm, convergence in a finite number of iteration round. And even more, the nice thing is that really here you can consider any arbitrary protocol asynchronous. You just need some connectivity on the long run, but that's natural. So the beauty of these methods is really this one. So then recently, with some of my students, we started to play with a mixed integer version of this problem. We figured out, again, you go to the centralized literature and you see that people what do is they somehow consider a convexified version of this constraint. So here I'm assuming that in the horizontal axis the decision variable is discrete, in the vertical one is continuous, then the feasible set is the union of all these lines. If you draw the convex solve, then you get this one, and you can show that if you solve this one and you find a vertex solution, then you can find a solution which is the same as the mixed integer program. So what people do is they start to add cutting planes to compute this convex solve. And again, we try to emulate the same in a distributed setting. So we basically assumed to have some basis of a problem relaxation to start adding cuts. So there are these cuts called Gomori cuts. We had to add also other cuts based on the cost. But then what you do is the same. So you collect all of them. You solve a relaxed version of the mixed integer with these local constraints. You find a new basis, and again, you do cuts, and you proceed. And what we were able to show also in this case is that you have this finite time convergence. First, we had to assume that the optimal cost is integer, but then we generalize it to general MILP, but getting some epsilon suboptimality. So we had to tolerate some error that you can decide somehow. I will go very quickly on this slide just to mention that there are uncertain versions of these problems. People that work, for example, in randomized algorithms, scenario approach, they know perfectly this setup, and it's very, very interesting to address it in a distributed way. We just did it recently. Let me go to the third part then. So this constraint-coupled setup. So in this constraint-coupled setup, I will show you how to use some decomposition scheme. As I said, there are also schemes like this one in the cost-coupled one. We use this primal decomposition idea. So let me first recap the problem. So you have the sum of n functions. Here we are assuming that the functions are convex. You have local constraints. We are assuming that the local constraints are convex and compact for our work. And then you have your coupling constraint. So the idea that, oh, by the way, let me point out that this problem has been addressed not so much as the previous one. So there is really probably even more work to do on this setup, which again is very close to our application. So I think it's really interesting to address. So, okay, so let me try to describe you this primal decomposition idea, so to give some intuition. So this coupling constraint says that you have some total resource, this B, and you want to find decision variables such that these allocations do not exceed the total resource. What people started to do in optimization in a centralized setting is the following. So let's pretend that this allocation, this resource B that I have, can be partitioned in n sub-resources, local resources. If somehow I know how to split the total resource, then the problem becomes much easier because I can solve independently those problems, just enforcing that I don't exceed the local resource. So if each ai of xi does not exceed yi, then I sum them, they will not exceed b. Very simple, okay? But now the problem is, how do I find these y1, yn? And in fact, if you look at the solution of this optimization problem, this local one, it depends on yi, and you can call this cost as pi of yi, so a function of yi. And then what do you do? Okay, so you have this pi of yi that come out from this problem, then you can have a so-called master problem in which you minimize the sum of all these pi yi, subject to the fact that these local resources must sum to b. So you have a master problem and subproblems, and this is a classical parallel structure, and there are algorithms that solve this in a parallel way. Let me mention that there are these constraints here that I don't want to say too much, but they are here because you can have this problem infeasible when you fix yi. So if you assign to I a little resource, then due to this constraint set, it may be that it doesn't find any solution. So you need that, but let's forget this one for a second. So we have this problem to solve. It's a constraint problem with this nice equality constraint. And you can show that if you apply a projected gradient or a projected subgradient to this problem, then you can explicitly find the update. So the update is the following: yit plus 1 equal to yit minus some step size, and this is basically the projected, let's say, subgradient, or this is the projected version. Okay? So if you want to solve this problem, then you need to update this one for each I and exchange gradients or subgradients that you can compute by solving this local problem. Okay, this is parallel. How can we go to a distributed setup? So let me give you just some intuition. This is not the way we came out with the solution, but the intuition is the following. Here you have to sum j equal to 1n, and in a distributed setting, whenever we see j equal to 1n, then we substitute it with j in n I, just neighbors, because that's what you know. Okay? So then each agent I needs to solve this one and needs somehow to solve this local problem, because solving this local problem gives you a subgradient here. The problem is that now there are two questions to address. First of all, I said, okay, this local problem may be infeasible. What happens if it's infeasible? And the second one, how do I compute a subgradient? So to address infeasibility, what you can do is the following. If the resource is not enough, then you just allow violation temporarily during the algorithm. You allow violation, and you penalize this violation. So this is how we decided to address this problem. And then how can you compute a subgradient of this? It can be shown that if you solve this problem and you can compute a dual optimal solution associated to this constraint, then this gives you a subgradient. Okay? This is standard in the optimization literature. So you do that, and basically this becomes the distributed primal decomposition algorithm that we decided to, that we designed. Okay? The nice thing is that you can prove that not only you have convergence in the cost, but this sequence that the agents generate, so x1 generates x1t, it has every limit point converging to an optimal solution. So you don't have to use any other auxiliary sequence here. And this is some work that is going to appear in TCNS. We also did some extension to time-varying edges, but let me skip it. So another challenge that, okay, too boring. So another challenge that we addressed for this setup was to consider mixed integer programs. Why? Because, again, in many applications, they arise. So in this case, the local set is mixed integer, okay? So how did we address it? So we used, the idea was, and it's not our idea, but people started to think of it, is let's try to compute some suboptimal solution, but with some suboptimality guarantee. So we want some guarantee, and we want the solution to be feasible. And the way you do that is you consider a convexified version of this problem. And why do you consider this convexified version? Because then there is this nice theorem that says the following. So if you solve the convex version, then you find a solution of the convex problem. Then you are kind of lucky because n minus s of this solution are already mixed integers. So in some sense, for n minus s, you are already done. So s is the number of constraints here. N is the number of agents. So if the number of agents is much bigger than the number of constraints, you have a lot of solutions that are good already. So the idea is let's try to adjust the other ones. Other people in the community addressed it via dual decomposition. For example, Maria and her group did that. We had this primal decomposition idea, so we said, okay, let's look at this other counterpart. And the idea is the following. Since you are solving the convex version of the problem, and you know that some of the solutions will not be mixed integer, you will need to adjust them, then you say, let's pretend that you have less resource. So let's put a restriction on the resource. Why? Because then, when you have the ones, the xi that are not mixed integer, you can violate, you can allow a violation, and if you have carefully chosen the sigma, all these violations will not exceed the total resource. Okay, so that's what we did, and the idea was, okay, let's apply in a distributed setting the distributed dual decomposition to solve this problem here, and then when we get the resource, let's do this adjustment and let's get a mixed integer solution. And we were able to prove that if you run the algorithm sufficiently enough and you stop it in finite time, plus you add an extra restriction, then in finite time you have feasibility, so you satisfy not only the local constraints but also the coupling constraint, and then we could compute some suboptimality bound in which there is some error due to the convexification, some due to the restriction sigma, and some due to the distance that you, to the fact that you stop at time t. We ran some simulation, and it was nice to see that probably due to this idea of resources, we were getting very nice suboptimality bounds. So in many cases, we were kind of optimal. So probably because the idea of restricting due into the local resource, it's really a good one. Okay, so let me go to the conclusion. Before doing that, let me give some perspective. So is there work to do in this area? I believe that there is a lot of work. So on the short run, for sure, you can just think of those network and optimization challenges that I mentioned and look at those setups. There are really still many interesting problems to address. So in this short run, there is really still a lot to do for in finding algorithms. Another, let's say, medium-term range of work is, I think, much more interesting, and is the fact of looking at existing protocols from the perspective of system control tools. So we started to do some work when I moved to Bologna, so it's nice when you start to interacting with new people because you find people with a different background. For example, in Bologna, there is Lorenzo Marconi that is really an expert in regulation. So we started to interact, and we figured out that if you start to interpret algorithms from the point of view of a regulation problem, then you start to gain a lot of insights, and even in the proof, you start to get much nicer proofs. And then if you consider problems that change over time, that becomes even more interesting. On an even longer horizon, I believe that there is really a huge amount of problems to solve when you go to optimal control of these complex networks. Because when you go to complex networks, there are setups that arise like the one that I show, but there are also other setups in which agents are entangled, and if the dynamics are non-convex, there is nothing out there, and there is really a lot to be done. And on the other side, if you start to think of what people have done, have talked about in the sessions, or even the other friends that did the plenary the days before, now there is this idea from machine learning of using data in the control that has a lot of challenges in classical systems. So think of complex systems, how many challenges there are out there. My point of view is that we should not try to move toward data-driven. So we have a background in model-based. So we should try to be careful and combine this model-based background that we have with data-driven. So let's not just move there, data-driven, and do that. But let's combine them, because that should be the best. I mean, some flavor of what I think as a possible direction. So if you are interested in some of the work that we have done, there is the project website that you can look at. Some acknowledgement. Let me thank people in the project group. In particular, these guys are here with me, are now with me in Bologna. The other ones started with me in Lecce, and now they are almost finishing, or they have finished. A special thank to Ivano, Andrea, and Andrea for helping me a lot in designing these slides. As you saw, there are very nice images. It was not my expertise. I mean, they helped me a lot, especially Ivano and Andrea. And then let me thank a lot of collaborators. It was really a pleasure in this year to collaborate with people and come out with nice works. Many of them are not in this talk, but you look at all these people, there are nice works we did together. And in particular, let me mention these 4 young guys here that were somehow some mentors, not just collaborators for me, especially when I started to move in this world. So really, I want to thank them a lot. I just go very quickly to the conclusion. So let me just mention that we just wrote a survey paper on distributed optimization that is going to appear in Foundation and Trends of System and Controls. It's on archive. We put it on archive. So the idea was if someone wants to start to play with distributed optimization, instead of looking for like 20, 50 papers and try to find what are things to start with, let's give some initial path to that. With this, I think I'm done. So thank you very much for being here.
So thanks very much, Giuseppe, for this very nice introduction to network-land optimization. And we have time for a few questions if you have. Thomas.
Thank you. Thanks so much for this beautiful presentation. I would like you to comment on whether there are connections with the very old works of the 70s and early 80s in team theory, the works by Lariot, by John Tsitsiklis. They did a distributed parallel optimization as well. And then there was this Witzenhausen counterexample that shows that even with 2 agents, linear system, Gaussian assumptions, you get very fancy. So the linear solution is not optimal, and all these challenges that actually seems to me still there. So I guess there are many connections with that, and if you have comments.
Okay, so I don't know this counterexample of this problem. I will definitely go and look at it. What I can say is, yeah, there is a lot of work by Bersekas and also Tsitsiklis on this. So in the majority of those works, even though sometimes the word distributed is used, they mean distributed in the sense that there is some computation that is allocated on some problems, but then many times they keep the master program, so they have a master. There are also there is a lot of literature in which they use the wording distributed. Maybe they don't have a master, but still maybe they design the protocol. So they say, okay, my algorithm should be such that this agent communicates with the next one maybe, and the next one, and so on and so forth. So whereas for us, when we say distributed, we mean really that you have like your smartphone and you want to do some processing of data using data from the other, but you don't decide, I communicate with you or with her. Maybe you have the opportunity, you communicate at some time, and then you don't communicate, and so on and so forth. I think this is the main difference. For that other problem, honestly, I don't know because I haven't looked, but I'm very curious to see what is the problem.
So thank you, Giuseppe, for a very nice talk. I would like you to comment on problems where you have coupled equality constraints, which usually arise when you have dynamical systems which are coupled, which are coupled to the dynamics.
You mean the third setup, right? The constraint coupled, but instead of inequality constraint. Yeah, that's a very, very good question. Yeah, definitely that needs to be addressed. You may think of saying, okay, let's try to relax it to an inequality, but then you have to be careful if you get the same solution. But yeah, definitely that's a challenge to address. Absolutely.
Pass the mic directly to the neighbor. No? Not interested anymore? Okay. Other questions? Anybody has? I don't see any. Oh yeah, Moritz, please.
Also, thanks from my side. I would like to ask how much you could accelerate actually some of your algorithms by allowing centralized aggregation.
Oh, that's
and
a
such
beautiful
things, in
question,
particular for
Moritz.
the mixed integer part.
Yeah, that's really a very, very beautiful question. Yeah, I think that's a point that we need to address. So in the last 15 years, when we played with distributed computation, we make the standing rigorous assumption that you have one-hop communication and you communicate only with neighbors. So I think that if you really want to go to applications nowadays, this is probably restrictive. So I mean, you have clouds around, you have like powerful workstations. So absolutely, I think that's another very interesting direction to go. So try to mix the parallel algorithms with the distributed ones. So maybe you have agents that communicate locally, but then from time to time they try to speed up by using the cloud or by using the workstation. Yeah, absolutely. That's a very interesting point.
Okay. Any other questions? If not, then Giuseppe, you are getting also from the organizers a very nice present. Thanks very much.
Thank you very much.
Thank you very much again for a great presentation. So, but please